Okay, a quick video on instrumentation systems. So first of all, we've got to obviously recognize that we need to sense analog information and make some and get some meaning from it. So we can have some sort of resistive sensor. That can be an LDR, it can be a thermistor, or it can be a strain gauge, or whatever else you want it to be. And we're then going to potentially have a variable resistor here so that we can adjust what our output accordingly to the conditions that we want to be able to read. And of course our voltage out is going to be we're measuring across the that variable resistor, so as a ratio method, variable resistor over our resistance of our sensor plus the variable resistor times by the V supply. If we have some numbers with that, if I say that this is 500 ohms, and this is 1.5k, and I make that 5 volts, then in this case V out is going to be 1.5k over 500 ohms plus 1.5k times by 5 volts gives me 3.75 volts, and you all should be familiar with that, with doing something like that. Now the problem with this circuit in itself, and it's a brilliant circuit in itself, is the effectively simplicity. Is the output voltage may change or vary without a change in conditions. So the temperature may not change, the light may not change, but the output voltage does change, giving you a false indication of a change. Now, why is that? Well, it could be due to a power supply fluctuation, or what's called environmental conditions. As the circuit has been on for a while, the current's flowing through components. The components are going to heat up very microscopically because of the current flow, and because of the current flow, then they'll behave slightly differently. They'll have slightly different resistances. They'll have slightly different resistances. Then we're going to get a slightly different output voltage. Now, to fix this is quite simple. We just use two sensors, and we call that a balanced bridge. So we have two sensing circuits, one acting as a reference output and one doing the measuring, exposed to the measuring. The idea being is if we've got two, they will be exposed to the same power supply, same power supply fluctuations, and potentially the same environmental fluctuations, so we can use that to cancel each other out. So there's two ways of drawing the circuit. So if I give you an example, and obviously it's my favourite way because obviously it's the way that you probably understand it, so I'll just draw it quickly like this, and then I'll sketch in, pause the video and sketch it in the is that if we've got two sensing circuits like so, and we'll call that P and we'll call that Q. We'll use thermistors, make that a variable resistor, and that can be just R, and that's a variable resistor, so all labeled up. Okay, V2, V1 is the center points of those resistors. So we can have two sensing circuits, and we're going to get a voltage from the two of them. So let me just pause the video so I can then quickly sketch in the other one. So I've just quickly sketched in the other. So this is so it's often drawn like this. So it doesn't really matter which way we do it, but so what we do is so initially the bridge is what's called balanced. Sorry. Using the variable resistor, so that the voltage V1 is equal to the voltage V2. So they will have a voltage on them, whatever that might be, and we'll measure that in a minute. But ultimately, if they're the same voltage, the difference between them equals 0 volts because they're exactly the same voltage. And you can see on here, effectively, what we quite often do is measure the output voltage from across the two different terminals between that one and that one. Okay, but essentially we've still got V2 there and V1 there. It's exactly the same circuits. Now, because they're just potential dividers, then and they're balanced, then what we can say is the ratio of P to the variable resistor must be the same as Q as that thermistor's resistance to that resistance. Okay, so one thing that we can find out is some values. So if I say that thermistor P is 1.5 kilo ohms and thermistor Q equals 1.4 kilo ohms. Maybe they're just not, there's a slight difference between the two. The resistor equals 1 kilo ohm. We can find out what the variable resistor has been set to. It's just an academic exercise, so if we pop those values into our formula, then we can see that we've got the 1.5 over the variable resistor over the 1.4k divided by the 1k. Now, because I've used 1k, it's nice and easy to do it. 1.4k divided by 1k is going to be equal 1.4. So I've got the variable resistor is then going to be 1.5k divided by 1.4, gives me a variable resistor value of 1.07 kilo ohms. Okay, so that's the bridge as it's initially set up. We set it up so that the two output voltages are exactly the same, so the bridge is balanced. Now we then expose one of the sensing circuits to the conditions we want to measure, and the other one acts as a reference. So the other one is just left on its own. So this one would be if we could have one of them in a fridge and one of them not in the fridge. So let's take that scenario. After being balanced, Q is used to measure the temperature in a fridge, and then so Q is now reading 1.6 kilo ohms. So what we want to do is, well, what's the difference? So let's do this as a structure it. So what is V1? what is V1, V2, and therefore V out, our output voltage. Okay, so V1 there, we've got V1, which is the thermistor and the resistor. The resistor is 1K, and we're just told that Q has changed. So I don't think I told you a supply voltage. So let's say that we've got a supply voltage of 5 volts going into the circuit. So V1 is going to equal to sorry, V1, which one is V1 I've got as the resistor value, so V1 is 1K over 1.6K plus the 1K times by the 5 volts. Yeah, which equals 1.92 volts. V2 then is our reference watt, is our reference. So V2, so it's P, so P is 1.5K, and we'd set the variable resistor to 1.07K. So 1.07 kilo ohms over 1.5K plus 1.07K times by 5 volts equals 2.08 volts. So now we want to know what the V out is going to be. Now let me just go back to this drawing here. We want to know what the output voltage here is. So you know V2 is V2 is there, V1 is there. So in terms of a picture, our output voltage then, so we've got V2 is at the bottom. So we've got 2.08 volts just here, and then just at the top there we've got 1.92 volts. Okay, and so we're looking at what the difference is between the two. So 1.92 minus the 2.08 equals minus 160 millivolts. Now, and obviously, if that was a little bit much for you, let's think about it. You know, if I had a 5 volt supply across a resistor here, then you would say that the voltage across that resistor is going to be 5 minus 0, which equals 5 volts. Of course you would. And just obviously if I then change the lower voltage there to be say 1 volt, then the voltage across that resistor is 5 minus 1, which is only 4 volts. So we're doing something here that you do naturally, but now you're being forced to it. It feels a little bit alien to you. So what we've done now is, now we're having a balanced bridge circuit. We've now got a circuit that will actually give us a more reliable voltage out, the difference between the sensing and the reference of when conditions change. But because we've now got two signals, we need to actually feed that into something else. But whereas we only had the one signal before from one sensing circuit, you could put that into a logic gate, or potentially more like a comparator. We're going to have to use what's called a difference amplifier. So our difference amplifier compares the two different input voltages. How do you draw a difference amplifier? Well, you start with an inverting amplifier. So start with an inverting amplifier. So I've got a feedback resistor, RF. I've got an Rin, like so. Okay, but that only gives us one one input. So I'm going to draw it again. So I've got a second input. Let's draw it there like so. And effectively I need to mirror what I've got, so I'm going to have another RF down there like so. Okay, now and that's R in like so. So what you can actually hopefully can gather from the diagram here, that these two resistors are going to be exactly the same size, and these two resistors are going to be exactly the same size. You can call these two inputs whatever you like. Okay, now the output voltage that we're going to get is the difference, voltage difference that we've got on our input multiplied by the gain. Okay, and it is RF and Rin that define the gain, and it's just going to be RF divided by Rin. So if I went for 100k, I went for 25k, that means that would be 25k, that would be 100k, so therefore I'd have 100 over 25, which equals a gain of 4. Now some of you are obviously thinking, well, you started off with an inverting amplifier, well, where's the minus sign gone? Well, we don't have to worry about it if you can remember this formula. So how do we then take that forward? Well, V out is the voltage difference multiplied by the gain. So if we use what we had before, if we had we did have 2.08 at the bottom, didn't we? Yeah, so V2, so we did have 2. Beg your pardon. So if we make, so if A is 2.08 volts and B equals 1.92 volts, that's what we got. So we keep their positioning from where they were before. The voltage difference, use the sign on the op amp. So what do I mean by that? Well, okay, so going in on A, I've got 2.08 volts going into the non-inverting terminal, and then I've got on the inverting terminal, so minus, I've then got 1.92 volts. Okay, so that's my voltage difference multiplied by 4, which is the gain, apologies for that bing, equals 640 millivolts. So that's why we don't have to worry about the minus sign, because it all gets taken care of with our circuit. So that's our difference amplifier. So hopefully that was okay. So that we're on to the home straight now. We're looking at movements. So we've got what's called a slotted disc. So a slotted disc is used for speed only, and it's things like fans, things like that, that's got blades and they've got holes in them where light can shine through. And we use what's called an opto-isolator circuit. Now an opto-isolator circuit is just some sort of light source like an LED or something like that, that then it shines on to a phototransistor. So that's a phototransistor. The whole thing is called an opto-isolator. So if I then measure V out just there, when we block the beam, and if I could put some voltages there, then the phototransistor doesn't conduct, so V out is 5 volts, it's a logic high, and when light shines on the phototransistor, then it's going to conduct fully, so V out is approximately 0 volts, so a logic low. So we get and all we do is we have our slotted disc sits in between the two, so it's cutting the beam all the time. So if we have an example where we've got 20 slots in our disc, and we get 120 pulses from the opto isolator in 2 seconds. What's the speed of what's the speed? RPM, revolutions per minute. Well, first of all, there's a couple of different ways of doing it, but so I obviously look at rotations. So we've got 120 pulses, and there's 20 slots in that disc. So that means that there will be 60 rotations in the 2 seconds. Okay, now revolutions per minute, we're in seconds, so we then need to say, well, okay, so therefore, whatever way you want to do it, so therefore there's going to be 1,800 in 1 minute, which is another way of just saying 1,800 RPM. But that type of system will only measure speed. If we want to do then position, then we need to use what's called an encoded disc. Now, we don't use a binary patterned disc, because more than 1 bit changes at a time, and this may give an incorrect false output from incorrectly placed sensors. When I show you the disc in a minute, you'll see that because as you go in towards the disc, then the sensor positioning needs to change, and it's very difficult to position the sensors so you can get it exactly right. So if I give you an example where we're going from quite simply from what it would be binary 1 to 2, something like that, the result could be is that this second bit here could change whilst the first bit is still a 1. So what we could actually end up with is going from that, and that second bit changes to 1 while still the first bit there is still a 1 before we get to that. So we end up with an extra reading which is incorrect. So what we then do is we use what's called grey code. Okay, so with grey code, what we do, we only change one bit at a time. So let's see it as a truth table to start with, It's set to the start of the truth table. So and the ruling is you change the least significant bit unless that code has already occurred, and if not, you leave that bit alone, and then try and change the next least significant bit, and you work your way in. So that's what we've got. So we can go to that. That's fine. Okay, but we're only changing one bit at a time. So I can't change the least significant bit on this now because it takes me back to that code. So I'd leave that least significant bit alone, which means I could change the next least significant bit. Going down to this, if I was to change the least significant bit, would I have had that code before? No, so I can make that a 0 and then leave that bit on its as it stands. Right, moving down. If I change the least significant bit, would have had that code before? Well, yes, I would have had that code before. Okay, so I can't change it. If I change that least significant bit, will I have had that code before? Yes, because it will give me all zeros. So I'm going to leave it alone. So therefore, I'm then going to change the next least significant bit. Next line, can I change the least significant bit? Would I have had that code before? No, so that's that line done. Can I then change the next least significant bit? No, I can't change that least significant bit, so I've got to leave it alone. Can I change the next least significant bit? Yes, I can change that one there, so we've got that. Right, we're onto the home straight now. So can I change the least significant bit? Yes, I can, because we haven't had that code before. And then finally, if I change that least significant bit, I've had it, so I leave it alone. If I change that least significant bit, have I had it? No, leave it alone. So effectively, we're back to where we came from. So that is the end of my 8-bit sequence, like so. I don't need to go onto that line. Okay, so that's it in a table. Then if we're drawing it on a diagram like this, and this is where you can see how tight it gets with placing sensors. So we go for something like that. Okay, so drawing this in onto here, so that there is going to be my least significant bit. So moving in, so changing the least significant bit. Okay, changing can't change that, so keep it the same. So changing the next one. Now I am doing this without looking at the table, but hopefully we should then correlate from the table. Like so. Yeah, there we go. So the idea is you change the least significant bit unless you change that unless that code has already appeared, and then you try and change the next one by leaving the previous one as it stands, and hopefully those two should agree. So only one bit changes at a time. Now I know you can see it on here, but the number of segments equals 2 to the n, where n equals the number of bits. So i.e. with 3 bits here, we've got 2 to the 3, which equals 8 segments. So hopefully you can see that in the picture. Now, one last thing we've got to do was how accurately can we look at the position. So we've got resolution. Now the formula for that is the disc degree, because we might not always have a 360 degree disc. So if we have a 90 degree disc, something like that, and 3 bits the same, then our resolution is going to be 90 over 2 to the 3, which equals 11.25 degrees. So that means we can accurately measure in 11.25 degree steps. Okie dokie, and hopefully I know that was quite quick, but that's the end of this video.